Hello everyone, welcome to another video where we're going to cover in depth the solution for an in-class problem. Today we're going to cover the solution for the very first exercise that we find in our lecture. So this is for lecture 1.3 and it's an exercise about the construction of truth tables. So in this particular exercise we are discussing the XOR operator, which is very similar to the OR operator except that it implies mutual exclusivity. What does that mean? Well, that means that if I have a compound proposition as this one here, A XOR B, what that is saying is that at least one of these two has to be truth, but only one of them. They are mutually exclusive. In the case of this particular exercise, this is just for the sake of making our truth table simpler, this compound proposition is going to be referred to as X. So this here is X. And then we are given 4 possible truth tables, and we are asked to evaluate which one of them is the actual correct truth table to talk about X. So let us review each of those tables. So the first table that we're given looks a little bit like this. Hopefully, we can already see from the very setup or the very way in which this particular table is designed that this table has to be wrong. Why is that? Well, because of the way that the values of truthfulness have been put together for the A atomic proposition and the B atomic proposition. And that has caused us to have 2 cases where A is true and B is false, and 2 cases where A is false and B is true. In other words, we are not seeing here correctly represented all possible combinations. There is not an instance where both are true at the same time in this table, nor there is an instance when they are both false at the same time. And so what that leads is that now these 2 results are contradicting each other. So in one case, I have that A is true, B is false, and XOR is true. And in the other case, I have that A is true, B is false, and the XOR is judged to be false. So again, these are contradicting each other. This table is poorly constructed, so we would discard it immediately. So our B truth table that we have to judge looks a little bit like this. Again, from the get-go, we might be able to detect the fact that this truth table was not constructed the way that we were taught in class. So in class, we were taught that the first atomic proposition should have half of the values being truth and false, and then divide those halves into halves to assign the truth values of the next atomic proposition. However, we are going to ignore that fact because if we were to reverse these 2, if instead of writing A first and then B, we had B here and A here, we would have satisfied the order. And really, A and B, like the particular order in which they appear is not that relevant. We still have an ability or a chance to evaluate every possible combination. So we have both being truth here, both being false here, and here the 2 possible scenarios with only one of them is true. So now we are able to judge whether these values here have been assigned correctly. And then we are told that what the XOR connective implies is that we have a scenario where we have competing, mutually exclusive events where one of them, at least one of them, has to be truth. And in here, we can see directly that this definition is violated here because in here we have a case where both A and B is true, and our XOR operator is given a value of truth, and that goes against our definition that we had here. Similarly here, we can see that these 2 scenarios were actually correspond to what the XOR indicator means because there's only one of the true atomic propositions being true at the same time, and yet the XOR operator is assumed to be false. So again, this is also incorrect, and altogether we would discard this table. So let us look at the third table. Okay, so now we can see the way in which these values have been assigned coincides with what we learned in class. So we have 2 truths here, 2 false, and then true, false, true, false. That's perfect. And then we can also see here that in these cases, the XOR operator is given the value we would expect. So here we have a case where only A is true, and here we have a case where only B is true, and both have correctly been identified as being truth for the XOR operator. However, in this case, we have that both of them are truth at the same time. And again, that goes against the mutually exclusive component of how we have defined the XOR operator. So this is wrong. So this table is also incorrect. And we go to the final table. So our last truth table looks a little bit like that. Again, we notice here that the way that this truth and false values has been assigned corresponds to what we discussed in class. Similarly here. And more importantly, we see here that again, we have kept here the correct interpretation of XOR. So only A is true here, only B is true here, corresponds with our definition. But more importantly, we now see that here, where both atomic propositions are true at the same time, or XOR operator is correctly given a false value, again, because only one of them should be true at the same time. And in here, where neither of them is true, we correctly identify it as being false, because again, the XOR operator indicates that at least one of them must be true. So that is the solution to this very first in-class problem.